The past couple hundred years, we've called a lot of things the November Revolution. As far back as the 1830s, when Poland rebelled against the Russians, you had the famous October Socialist Revolution that technically took place in November if you use the Gregorian calendar. You then have the creation of the Weimar Republic in Germany following World War I, and most recently we've had the 1989 Velvet Revolution, which ended the communist rule in Czechoslovakia, the same month that the Berlin Wall fell. But I'm here to talk about November of 1974. The United States is coming to terms with the resignation of Richard Nixon just a few months prior. The midterm elections of 1974 under Gerald Ford were a slaughter for Republicans. Democrats stole an astonishing 49 seats, securing the two-thirds majority that they needed to override Ford's presidential veto powers. In the nearly 50 years since, it remains the largest net gain of seats for the Democratic Party. But no one calls this the November Revolution of 1974. That name belongs to a decidedly non-political event. Physics is about to experience a coincidence so remarkable, so improbable, that we're unlikely to see anything like it ever again. By this point, most of the physics community was in agreement that atoms were made up of three things: a dense nucleus of protons and neutrons, surrounded by a fuzzy cloud of electrons. And all of the observable matter in the universe was just combinations of these three ingredients. But by the 1960s, there were those who suspected that maybe there was a level even deeper than the subatomic, an even smaller set of particles that made up the protons and neutrons. Quarks, as they were called, supposedly came in three flavors: up, down, and strange. And despite some experimental evidence in favor of this quark model, it was still up for debate whether quarks were actual physical particles or just useful mathematical concepts that helped to resolve some of the weirdness of certain experiments. Sure, they fixed a few problems here or there, but they seemed like a band-aid applied to what was a huge hole left in the jigsaw puzzle. But this attitude would change thanks to an unexpected result off the California coast. Bert and Richter was leading a team at Stanford, working on their newest $6 million toy, a tunnel loop 80 meters in diameter known as SPEAR. This is a very expensive tunnel in which electrons and their antimatter equivalents are rammed together at high speeds in the hope that they'll explode into new particles. As is typical in physics, when a breakthrough is made, everyone assumed that something must be broken because they weren't even looking for a new particle. And yet, there it was, flashing into existence for just 7 zeptoseconds, with an energy of 3 billion electron volts. This wasn't evidence of the up, down, or even strange quark. This was something new. This was a fourth quark. Specifically, a fourth quark appearing in tandem with its antimatter equivalent before they annihilate each other. Now, a fourth quark had been proposed before, but never seen in the wild. If this truly was the fourth quark, CHARM, as it's now called, the band-aid could come off. They had just found the missing jigsaw piece. Richter had wanted to name the hybrid particle SP, after the accelerator that had discovered it, but his co-workers really didn't like that name. So instead, he asked a Greek colleague which Greek letters were still available. Iota was free, but he opted against it since iota is a synonym for insignificant and it seemed a little counterintuitive given the magnitude of this discovery. So in the end, he settled on psi. Later, they would observe the path the particle took using a spark chamber. A spark chamber is a stack of high voltage metal plates filled with helium and neon. When a high-energy particle passes through it, the gas ionizes, leaving a visible trail of sparks. And somehow, the spark trail was the exact same shape as the letter psi. Now, this fact on its own is crazy, that a particle was named and then very soon after resembled the shape of its name. But this wasn't the coincidence I mentioned earlier. That exact same month, on the opposite side of the country, a group is working out of Brookhaven National Laboratory on Long Island. Leading the team was Samuel Ting, and with their own collider, the larger and more powerful AGS, they had stumbled onto the exact same charm-anti-charm particle. Ting called the particle J. As the story goes, he chose J because it's remarkably similar to the Chinese character in his own name. Other stories behind the name have cropped up over the years, but if I had to choose a personal favorite story, it's that J is the first letter of his daughter's name. On the 11th of November, Ting flew to Stanford for unrelated reasons and just happened to cross paths with Richter. When both men excitedly told the other about their recent breakthrough, they soon realized that they were talking about the same thing. Later that same day, they jointly made the announcement for the discovery of J/psi. It's astounding that such an important discovery was made independently within such a short period of time. For this reason, J/psi is the only subatomic particle that has two officially recognized names. But we don't call it the November Revolution because of one discovery. We call it that because it pointed the whole field in a specific direction, kicking off a decade of discoveries. That same year, Jean Iliopoulos would compile what is now widely understood to be the first ever edition of the Standard Model of Physics. At this point, it's an even larger jigsaw puzzle, still missing some critical pieces. And you know how jigsaws are. Even if a piece is missing, you can still kind of infer what it should look like. Maybe you recognize some of the names here. This outer ring we call the fermions, aka the matter particles. The top half is the family of quarks. Note that you'll never find one of these on their own, only in larger combinations called hadrons. Only 3 years after the discovery of charm, the first evidence of an even heavier fifth quark was found. This new one was named the bottom quark. What this suggested was that there is a sixth partner quark also out there, waiting to be found. And thus the search for the massive but elusive top quark had begun. Gotta tell ya, this is one hell of a naming convention. On the other side here we have the leptons. Unlike quarks, you can actually find these alone in the wild. They consist of the electron, who you may recognize from their greatest hit, electricity. Less well known are its big sibling, the muon, and the even more recently discovered, even bigger sibling, tau. Each of these three have their own corresponding pets, the neutrinos. One of them is still just implied, but we're pretty sure it's out there. Moving on inward, we have another class of particles, the bosons. If fermions make up matter because they're firm, then the bosons make up the four fundamental forces. I don't have a mnemonic for this one. The photon you've probably heard of. It's responsible for all light and EM waves. You can thank Einstein for that one. At the tail end of the 1970s, the gluon had popped up in experiments. It's responsible for gluing together quarks to make protons and neutrons. The other two here are still missing in action. You have the W and Z bosons, which supposedly control nuclear radiation and decay. Their existence was so certain, though, that theoretical work suggesting them had already won a Nobel Prize. And that's about all there is. That's the Standard Model of Physics. Well, okay, no, not technically. There were those who proposed another boson, one that would tie all the other particles together in a field. And this field would supposedly explain the origin of mass. At this point in time, it wasn't so widely accepted, and thus its time in the spotlight will come much later on. So, as the 1970s gave way to the 1980s, this was the state of the Standard Model and most of particle physics. But something was becoming clear. To make further progress and find those missing pieces, the technology needed to catch up first. The heavier the particle, the higher the energy needed to produce it. They needed bigger accelerators. And thus 14 years after their first joint announcement, Burton Richter and Samuel Ting will be reunited. Not for the first time. They had, after all, jointly accepted a Nobel Prize some years back. And yet, despite the prestige of the Nobel ceremony, this occasion was no less monumental. A few feet away from them, the announcement is being made for what will be the largest scientific undertaking in United States history. It would be the particle physics equivalent of landing on the moon. Their mission was to find the holy grail of particle physics. And Ronald Reagan was all in.
Outer space used to be called the final frontier. But today we've begun to tap another frontier, inner space, whose infinitesimal constellations hold out infinite possibilities. I know that some people may question the practical applications of the superconducting supercollider, but the truth is, the practical applications of this knowledge are already changing the way we live. In the face of ever-increasing global competition, the United States must maintain the leading edge in science and technology, and building the world's largest particle accelerator is a visible symbol of our nation's determination to stay out front.
Within 5 years, the project will have completely collapsed, and with it, American leadership in the realm of particle physics. Burton Richter would go on to call the project one of high-energy physics' greatest failures. I'm warning you now. This story has a lot of things. What it doesn't have is a happy ending. This was a failure so big, so massive in its scope, that it's hard to put into words. Instead, I think it's better if I let you see for yourself. If I gave you a rock and asked you to describe what the inside of it looked like, with no access to fancy tools, what would you do? Personally, I'd throw it at the ground repeatedly until it broke. At some point, humans realize that the best way to find out what something is made of is to smash it open. And if it's a rock or an apple, our hands can get the job done. But if we wanted to break apart something small, like a proton, for instance, we're going to need some specialized gear. Hence, particle accelerators. A particle accelerator, or more specifically a collider, consists of three main components. 1. A tunnel system, generally a circular loop that is held at vacuum and at temperatures close to absolute zero. This is what the particles will be traveling through. 2. A set of ultra-strong magnets. These serve two purposes. Most of the ring is surrounded by equally spaced magnets, and their job is to steer the charged particles around the ring. Additionally, you have a specific region where the magnets are used to speed up the particles once per loop, like a booster in Mario Kart. After thousands of loops per second, the particle has approached the speed of light. And finally, 3. The collision zone. This region usually contains an advanced detector that gathers hundreds of gigabytes of data per second. Think blood splatter analysis, only real. Modern accelerators are typically built in several stages, with linear injecting segments, multiple booster sections, etc., like the incremental stages of a rocket. But by and large, accelerators are just big guns we build underground, and then we shoot really tiny bullets, and then we hope that the bullets ram into each other and explode. Why? Because collisions release a ton of energy, and energy is related to mass through Einstein's iconic equation, E=mc². So, if you want to generate heavier quarks, we need larger energies and larger machines. And for the past 2 decades, one nation has been the undisputed world champion when it comes to building accelerators. Throughout the 60s and 70s, 5 quarks and 2 leptons were discovered in the United States, the fruits of the November Revolution. At the turn of the 1980s, the US was operating 4 major accelerator labs. You had SLAC over in California, where we met our buddy Richter, and you had Brookhaven in New York with our buddy Ting. You also had Cornell, a little ways away in Ithaca. But the newest and shiniest was the crown jewel of America's particle accelerators, the Tevatron, located at Fermilab in the outskirts of the windy city of Chicago. The Tevatron name is an amalgamation of 2 things. 1. TeV is short for tera electron volts, or a trillion electron volts. That's the approximate collision energy the machine is capable of generating. And the other half tron, because it's very funny to name expensive scientific instruments with the suffix tron. With a loop diameter of 2 kilometers and state-of-the-art superconducting magnets, the Tevatron was the world's first collider to break the energy barrier from GeV to TeV. That was the true final frontier. As the standard model began to get filled in, the missing puzzle pieces were beginning to take shape. That meant the top quark, the W and Z bosons, and maybe, just maybe, the Higgs boson. The United States and its highly decorated army of physicists wanted to be the ones to plant down that flag. Bring home that W. Now consider how many accelerators existed in the rest of the world. In Western Europe you had CERN, straddling the French and Swiss borders, and then also DESI in Germany. The Soviet Union had 2 accelerators all to themselves. And finally, the rookies on the scene, you had Japan with their Keck Accelerator Lab. You may have noticed here that the US has almost half of the world's major accelerators. And for a while that was a major strength of the Americans. But as the 1980s rolled around, this was turning into a weakness. See, the US budget for particle physics had to be split between 4 labs that varied in size, age, and capabilities. To keep each of them competitive would require multiple ongoing upgrades that would spread the slim budget even slimmer. The fear was that Europe's consolidation into one entity, CERN, would allow them to pool all their resources and take the lead. CERN was already digging a tunnel for its newest collider, the Large Electron Positron Collider, or LEP. With a diameter of 8.6 kilometers, it would be by far the world's largest, making Fermilab's 2 kilometers look quaint. To maintain their competitive edge, US physicists would have to one-up CERN. Instead of 4 small labs competing for funding, the path forward should be one new, giant lab, all their eggs in one basket. Throughout the 70s, there were conferences held over and over again with dreams of a VBA, or Very Big Accelerator. That name was coined by Leon Lederman, then the director of Fermilab and the leader of the team that had discovered the bottom quark. Generally considered to be the godfather of this hypothetical new accelerator, he would become the project's biggest cheerleader in the years to come. But concrete plans wouldn't materialize until 1982 at a conference in Snowmass, Colorado. Lederman again led the charge, calling for a new gargantuan American collider that would be able to support energies as high as 40 TeV with a loop diameter of 30 kilometers or higher. This was an absurdly high energy and a massive footprint to go along with it, and thus would require an enormous location to build it in, something flat and empty. The hypothetical machine was therefore nicknamed the Desertron. A year later, in 1983, CERN announced the discovery of the W and Z bosons. There were no buts about it, Europe had taken the lead in the boson race. With the pressure mounting even further, a government-sponsored panel was organized and the American project got its official name, the SSC, or the Superconducting Super Collider. A machine so grand and ostentatious, its name included the word super twice. Rough estimates pegged the cost of such a machine at somewhere between 4 to 8 billion in 2021 US dollars. Now look, I get that 1 billion is a big number. So big that it's basically meaningless without a reference frame. So I've assembled a few comparisons. The taller the height, the more expensive it is. We have the most expensive skyscraper ever built at 4 billion, the most expensive stadium ever built at 5.5 billion, and also the most expensive bridge at 7.5 billion. For a little mobile flavor, the most expensive plane is the B-2 stealth bomber at 2.43 billion, and the most expensive ship ever built was the USS Gerald R. Ford at 13 billion. For some scientific comparisons, we have the Mars rover at a humble 2.7 billion, the Human Genome Project at 5 billion, GPS satellites at 12 billion, and the Hubble telescope in at a hefty 13.5 billion. What about one of the largest American engineering projects of the 20th century, the Panama Canal? 19.7 billion. So overall, I don't think we're doing too bad considering this thing may or may not unlock the secrets of the universe. But still, there was only one way they were going to pay for a machine that expensive: the American taxpayer. And to be clear, each of America's previous 4 colliders were paid for the same way, but each of these had a comparatively baby budget of a few $100 million. Look at them, little baby machines. Don't get me wrong, it's nothing to scoff at, that's a lot of money. But when it comes to taxpayer-funded projects, there is a big difference in a price tag that starts with an M versus a price tag that starts with a B. Not only that, these 4 colliders were built during a period of American history that was far more sympathetic to the whims of physicists. How do I put this? Ever since they dropped the bomb on Hiroshima, the United States had supplanted itself ahead of Europe to become one of 2 global superpowers. And again, partially thanks to that very same atom bomb, America took the lead in another area: nuclear physics. Since World War II, nuclear and particle physicists have enjoyed a certain amount of privilege, not afforded to other subfields in physics. With the successful completion of the Manhattan Project, which, by the way, clocked in at around $30 billion in today's money, it seemed only logical to create an organization that would manage any future research into nuclear weapons. I mean nuclear energy. That led to the creation of the Atomic Energy Commission, or AEC. It was a confidential agency that had the luxury of operating largely out of the public eye, only having to answer to the Congressional Committee on Atomic Energy at meetings that were always held behind closed doors. For the most part, nuclear physicists were given a blank check to build powerful nuclear reactors and colliders on the pretense that their research was advancing national security. And particle physicists fell into two camps over this. On the one hand, you had the war hawks, people like Edward Teller and Harold Agnew, who actively championed the defense applications of nuclear research and were more than happy to enjoy the money they were being showered with. And on the other hand, you had the physicists who didn't much care for the war and weapons of mass destruction things, but they were happy to look the other way if it meant getting funding for their real passions. It's how the sausage got made, and no one was going to bite the hand that fed them. But this age of scientific free reign was about to change. The anti-war and anti-nuclear movement of the 60s led to harsh criticism of the AEC. It neglected radiation protections, reactor safety, and had a laissez-faire attitude when it came to environmental pollution. Congress was so fed up with the lack of oversight that they voted to abolish the AEC in 1974. The 1970s as a whole were a time of dramatic upheaval for America. It had been rocked by the Watergate scandal, and America's dominance in the automobile and electronics industries was waning, with Europe and Japan taking over. This, combined with unrest in the Middle East, had led to a global oil crisis, rampant inflation, and a massive recession. In response to this, President Jimmy Carter created a new department in 1977, the Department of Energy, or for short, the DOE. The DOE was organized to manage and fund research into a variety of programs, such as solar power, renewables, and synthetic fuels. Additionally, all nuclear responsibilities, peaceful or otherwise, were absorbed into the newly created department. No longer would their funding be automatically rubber-stamped. The DOE would be subject to the whims of Congress and the Public Subcommittee on Energy and Water Projects. The age of nuclear physicists always getting what they wanted was over. They'd have to compete for funding like every other subfield. So, as a first tentative step, the DOE approved a meager, I say meager in quotes here, $52 million to begin R&D in 1984. But if the SSC was going to turn that M into a B, they had to get some key people in Washington on board. They had to make a deal with the devil. The SSC only got off the ground due to an alliance of convenience. There had never before been a scientific project of this scope, both in the physical size and financial cost. Unlike previous American accelerators funded by the US government, this one was going to be the first to cross the billion-dollar threshold. In fact, it was projected to cross it a dozen times, and as a consequence, it was not going to be able to be quietly funded without significant public scrutiny. In particular, it needed the stamp of approval of one very specific person. There are two Ronald Reagan quotes often associated with the SSC, both of which came following a cabinet meeting on January 29th of 1987. At the end, when Reagan finally gave his approval for the project, he was told that his decision would make a lot of physicists ecstatic. His reply was, "That's probably fair, because I made 2 physics teachers in high school very miserable." But the other quote gives a little more insight into Reagan's thought process. Following a presentation on the merits of funding the project, he reportedly pulled out an index card from his jacket pocket and went on to recite a poem by Jack London. "I would rather be ashes than dust." This continued on for about a minute. In a moment that is very on brand for late-stage Reagan, those in the room with him were unclear on what he was trying to say. Reagan would clarify with a different quote, which he pulled from his days spent as a football announcer. He was telling physicists to throw deep. It was time for a Hail Mary. It may be surprising to you that Ronald Reagan, of all people, would be so enthusiastic about a multi-billion-dollar project that is incredibly abstract and with almost no short-term economic or strategic benefits. But I think the line "throw deep" perfectly encapsulates Ronald Reagan's distinct brand of Cold War posturing. It took nearly 6 years of delicate political maneuvering by physicists and bureaucrats alike to get Reagan to throw deep with the SSC and the Department of Energy. It was like playing political whack-a-mole. Every time physicists would gain one ally in Washington, they'd either retire or get promoted, only to be replaced by someone who wasn't that much of a fan of the project. But eventually, they'd manage to sway several key members around the big man himself. First was George Keyworth, a nuclear physicist serving as Reagan's first science advisor. Eventually, he was joined by Alvin Trivelpiece, the director of energy research at the DOE. He did a lot of the legwork to eventually get the support of John Harrington, Secretary of Energy. And Harrington was finally high enough up the bureaucratic food chain to arrange that fateful cabinet meeting where Trivelpiece gave the pitch that ultimately swayed Reagan. All of this is especially remarkable, given that when Reagan first took office in 1981, one of his first acts was to try and shut the DOE down. During his presidential campaign, Reagan had actively made promises to do just that. The department was the exact kind of red tape, big government overreach he villainized through his politics. As soon as he took office, Reagan slashed programs left and right and began to dismantle the department. He cut all funding to the renewable energy and synthetic fuel programs, and in a particularly spiteful and petty act, he removed the solar panels Carter had installed on the White House roof. You can see just how little Reagan cared about the department by looking at who he chose to run it. Throughout Reagan's 8 years in office, he would appoint 3 secretaries of energy, each of whom was uniquely unqualified. His first pick was a dentist turned politician. His next choice, Donald Hodel, was closer, as an ex-power grid administrator. And yet, he's most remembered for his proposed solution to the hole in the ozone layer, which was not to try and fix it, but rather suggesting that everyone just wear hats and sunscreen. His final secretary was John Harrington, a California real estate developer. Perfect. Now, hindsight has painted Reagan as anti-science, but I think this is a misconception. Reagan could be pro-science,